As we move forward with our understanding of forces in motion, we come now to the idea of work. What does work mean? Your parents probably yell it at you when you're lying on your couch, and Lord knows your science teacher often tells you to get back to work. But what does it really mean? Work is defined as a force being applied through a distance. It's important that when we use this term that we don't think about it as a force over a distance. Even though it sounds okay to say, if we begin to think about it that way, we might be tempted to divide the two instead of multiply them. What this means, though, is that if you apply a ton of force, but there's no distance traveled, no movement, then really no work is done. Yes, even if you try really hard and you get tired. So for work to be done, the force and the distance or the movement must be in the same direction. If you're carrying your backpack and holding it up against the force of gravity, then you're not doing any work when you walk with it to class. In this case, the force is up and the direction is forward. Therefore, the formula for work can be expressed as being equal to the force applied times the distance traveled, where the force is measured in newtons and the distance is measured in meters. The unit for work is the joule, which is another derived unit, as some of the others that we've spoken of, Newton being one of them. A joule can also be written as a Newton times a meter or a Newton meter. All right, so now you want to get down to work. There are two types of work we're going to talk about. First, we have to talk about work input. This is the work done when we use a machine. Here, machine always means simple machine, which we're going to talk a bit more about in a little while. The formula for work input is the same as the normal work formula, except we add some qualifiers. The force effort is the force you apply to the machine, and the distance effort is how far you apply that force to the machine. The work output is how much work you would have to be doing to do the same job without a machine. Remember, here, machine means a simple machine. So the force resistance is how much force it would have taken to move the object without a machine, and the distance resistance is the distance the object would have moved without the machine. If this is a bit confusing right now, just hang with me. It'll become more clear as we go on, and there's a lab for you to actually practice these concepts at the end. All right, on to the different classes of simple machines. Depending on how you categorize things, there are a differing number of simple machines. For our purposes today, we're going to talk about them as 6 different ones. First, the lever. A lever is a bar that rotates around a fixed point. That point is called the fulcrum. Examples of lever are things like a bottle opener or a hammer. Think about when you would use a lever and why. What part of your life does it take up? Next up, the inclined plane. An inclined plane is a sloped surface used to raise an object. In this case, the object travels a longer distance but requires less force to be lifted to the same height. An example of this would be something like a ramp to help a wheelchair go up, or even stairs. All right, next up, a pulley. A pulley is a wheel with a groove and a rope running over it. If you've ever sailed, you've used a pulley. You ever watched one of those shows where they're lifting a piano up to a second floor window and they're using a big rope to do it? Usually there's a pulley at the top of that system that's helping to pull it up through the high window. Think about how a pulley works. Now think about a lever. Can you see any similarities here? A wedge. A wedge is an inclined plane with 2 sloping sides that come together to form a point. Most often, wedges are used to split things. Think of an axe, or a sword, or your former best friend as you get too close with your significant other. Now things get complicated. A screw. What a crazy thing. Have you ever considered why a screw actually works? A screw is really an inclined plane wrapped around a cylinder in a spiral. It has the benefit of moving easily when rotated. Wait, did he just say rotated? That sounds a lot like a lever. But he also said it had an inclined plane. Crazy! Ready for more? How about a wheel and axle? Now we'll take the same principle as a lever or a pulley and marry it to a second wheel of a different size. Marriage, making things better. There's your free lesson for the day. With two different size wheels, when you turn one, the other rotates at a different speed. In the case of turning the axle, it causes the wheel to rotate a greater distance, but to have less force. Think of a doorknob or a faucet, or even the steering wheel on your car. All right, let's review. So the simple machines we've discussed so far are a lever. This is a famous example where someone once said, if you give me a lever long enough, I could lift up the entire world. An inclined plane, used to help you get up to a higher height if you're maybe not totally mobile. A pulley. A wedge for breaking things apart or splitting things apart. A screw. And a wheel and axle, in this case, a doorknob. Enough of these concepts, you say. I want some math. Well, here you go. Calculations with machines. Remember, we're talking about simple machines. Why do we use simple machines? What are they good for? Well, for one thing, they give us what's known as a mechanical advantage. The mechanical advantage is a unitless number that tells us how many times the machine multiplied the effort force. The formula looks like this, where the force of the resistance divided by the force of the effort is equal to the mechanical advantage. This serves to tell us how helpful a simple machine is. It's important to remember that since you're dividing newtons by newtons, the mechanical advantage should always be expressed as a number with no unit. It is a unitless number. And last but not least, efficiency. Efficiency is just like it sounds. It's a measure of how much of the force you put in is coming out the other side. Efficiency is defined as the ratio of the work output to the work input, or the work output divided by the work in. Okay? Work out divided by work in. As with mechanical advantage, this is a unitless number. And since we're multiplying it by 100, that number should always be expressed as a percent. One important thing when working with efficiencies, if you end up with an efficiency greater than 100%, something's probably not right. All right, I hope that helped to clear up some of your understandings about simple machines and give you some ideas about work. We're going to do a lab the next time I see you, and from there we'll be talking more about power. Thanks for watching.